Hello everyone, and welcome to this session about 3D point cloud subsampling. Today, I'll be talking about what point cloud subsampling is, why we need it, and how we can apply it to reduce the size and complexity of point clouds.
Point clouds can be very large and dense, with millions or billions of points, which can pose challenges for processing, analysis, and visualization. This is where point cloud subsampling comes in. Point cloud subsampling is the process of reducing the number of points in a point cloud while preserving certain properties or characteristics, such as distribution, density, and structure. Subsampling can be performed using different methods, which I'll discuss later in this presentation. The main goal of subsampling is to make the point cloud more manageable and efficient without losing too much information or accuracy. Firstly, subsampling can help reduce the computational and memory requirements of point cloud processing and analysis. When dealing with large or dense point clouds, it may not be feasible or practical to process or store all the points, especially in real time or on limited hardware. Subsampling can help reduce the data size and processing time while still providing enough information for the intended task. Secondly, subsampling can help remove noise or outliers from a point cloud that may interfere with subsequent analysis or visualization. Sometimes, point clouds can contain spurious or erroneous points that can affect the quality and reliability of the data. Subsampling can help filter out such points and improve the signal-to-noise ratio. Finally, subsampling can help simplify the geometry or structure of a point cloud for better understanding or communication. Point clouds can be very detailed and complex, which may make it difficult for non-experts or laypeople to comprehend or appreciate. Subsampling can help highlight the key features or patterns of the point cloud and convey the message more effectively. Now, let's talk about some common subsampling methods that can be used to reduce the size or density of a point cloud. There are many different subsampling methods, each with its own advantages and limitations. Here are some examples. Random subsampling. This method involves selecting points randomly from the original point cloud. Random subsampling is simple and fast, but it may not preserve the local structure or density of the point cloud and may result in uneven or biased sampling. It's often used for preliminary or exploratory analysis, where the goal is to get a quick overview of the point cloud without too much emphasis on accuracy or precision. Spatial subsampling. This method involves selecting points based on their spatial distribution or proximity to other points. Spatial subsampling can help preserve the local structure or density of the point cloud. However, spatial subsampling may require more computational resources and may be sensitive to the size and shape of the point cloud. Octree subsampling. This method involves recursively dividing the point cloud into octants and selecting one or more points per leaf node. Octree subsampling can help balance the trade-off between resolution and complexity by adapting to the local density and geometry of the point cloud. So, let's go to the practice part directly. If you have a huge point cloud with a lot of points, but you don't want to deal with such an amount of data, you can use a really interesting tool inside open source software Cloud Compare, which is a subsample. This tool allows you to reduce the number of points on your point cloud in order to better deal with it. Imagine you have a point cloud of a landscape consisting of millions of points that accurately capture every detail and feature of the surface. However, you only need a smaller subset of the points to perform a specific task, such as measuring the landscape dimensions or analyzing its shape and topography. Using point cloud subsampling, you can reduce the number of points in the point cloud while still preserving the essential features and characteristics of the landscape. The resulting subsampled point cloud would contain fewer points and occupy less memory and storage space, making it easier to process and visualize. However, the subsampled point cloud would still retain the critical information necessary for the task at hand, allowing you to perform your analysis or measurement accurately and efficiently. So let's do this in Cloud Compare. First of all, we need to extract a small part region of our point cloud on which we will work. Use the scissor tool to make the segmentation. Here I will make just a clone, so I don't touch the original data, even if Cloud Compare create, by default, a new subsampled point cloud. For instance, you could use the random subsampling method to randomly select a percentage of points from the original point cloud, or use the spatial subsampling method to select points based on their distance from each other. Alternatively, you could use the octree subsampling method to divide the point cloud into smaller regions and select one or more representative points from each region. The first method of point cloud subsampling we'll discuss is the random subsampling method. With this method, you have the ability to select the number of points you'd like to remain in the subsampled point cloud. You can specify this number directly or use a slider to select the exact number you need. For example, I'll choose to subsample my point cloud to contain 2 million points. But did you know that you can also subsample your point cloud using a scalar field? Instead of specifying a single value for the random subsampling mode, you can use the currently active scalar field to modulate the sampling distance with the scalar values. For instance, if the cloud is associated with a curvature scalar field, you can tell Cloud Compare to sample fewer points in curvy areas and more points in planar ones. Using the random subsampling method is a quick and simple way to reduce the number of points in your point cloud, which can make it easier to work with and visualize. It's important to note that the subsampled point cloud may not retain all the details and features of the original point cloud, but it will still provide useful information for your specific analysis or task. The second method of point cloud subsampling is the spatial subsampling method. With this method, you set a minimum distance between 2 points, and Cloud Compare will then select points from the original point cloud so that no point in the output cloud is closer to another point than the specified value. The bigger this value is, the fewer points will be kept in the subsampled point cloud. Here's how the algorithm works. Points are parsed in a somewhat arbitrary order, spatially organized by the octree. The very first point is flagged as to be kept. Then, for each subsequent point in the cloud, Cloud Compare queries its neighbors within the specified radius. If no neighbor point is already flagged as to be kept, this new point is also flagged as to be kept. In the end, only points flagged as to be kept will be part of the output cloud. Just like the random subsampling method, you can also use a scalar field to modulate the sampling distance with the scalar values in the spatial subsampling mode. You have to specify the sampling distance corresponding to the minimum and maximum scalar values, and Cloud Compare will linearly interpolate the spatial distance. The third and final method of point cloud subsampling is the octree subsampling method. With this method, you select a level of subdivision of the octree at which the point cloud will be simplified. In each cell of the octree, the nearest point to the octree cell center is kept. The higher the level of subdivision is, the smaller the cells are, and thus the more points you'll keep in the subsampled point cloud. By changing the parameters, you can adjust the sampling results to get the perfect subsampled point cloud that you are looking for. The octree subsampling method can be useful in situations where you want to simplify a point cloud while preserving its overall structure. Just like the previous two subsampling methods, you can also use a scalar field to modulate the subdivision level with the scalar values in the octree subsampling mode. So, to better understand the differences between the three subsampling methods, let's run a quick experiment. First, we'll create a planar mesh with dimensions of 10 meters. This mesh will serve as the basis for our point cloud, which we will create by randomly generating 1,000 points across the surface of the mesh. Now, this point cloud has a density of 10 points per meter square, which is actually quite dense. Typically, you would see much fewer points per square meter in real-world scenarios. So, to better visualize the differences between the subsampling methods, we'll run each of them and compare the result. Our goal is to reduce the number of points in our point cloud down to just 100. First, we'll use the random sampling method, which allows us to specify the exact number of points we want to keep. In this case, we'll set it to 100. This method will randomly select 100 points from our original point cloud, resulting in a new point cloud with just 100 points. Next, we'll use the octree sampling method, which subdivides our point cloud into smaller cells and keeps only the point closest to the center of each cell. We'll set the number to 100, which should give us a point cloud with about 100 points. Finally, we'll use the spatial sampling method, which allows us to set a minimum distance between points. This method will select points from our original point cloud so that no two points are closer to each other than the specified distance. We'll set this distance to approximately 73 centimeters, which should result in a point cloud with about 100 points. Try to repeat the process until finding the exact number of 100 points approximately. Here I found 103 points, so I will use them. Now, when we compare the results of each method side by side, we can see the differences in the density and distribution of the points. The octree sampling method gives us a fairly uniform distribution of points, while the spatial sampling method preserves more of the original density of the point cloud. The random sampling method, on the other hand, gives us a slightly more uneven distribution, with more points in some areas and fewer in others. Overall, it's clear that each method has its own strengths and weaknesses, and the choice of which method to use will depend on the specific needs of the project at hand. But by understanding the differences between these methods, we can make more informed decisions about how to subsample our point clouds and achieve the desired result. Now that we have seen all three methods of subsampling, let's dive into how we can further customize the subsampling process using scalar fields. Scalar fields are an important tool to use when subsampling a point cloud because they allow us to consider additional information when selecting which points to keep. By using a scalar field, we can tell the software to sample less points in areas where the scalar field is low and more points in areas where the scalar field is high. For example, if we have a scalar field that represents the curvature of the surface, we may want to keep more points in areas where the curvature is high, more complex, and fewer points in areas where the curvature is low, less complex. Using scalar fields can result in more accurate and efficient subsampling, as we are able to prioritize points that are most important for our particular use case. This is particularly useful when working with large or complex point clouds, where selecting points manually can be a daunting task. In addition to subsampling, we can also convert a mesh into a point cloud. Meshes are often used in computer graphics to represent 3D shapes and can be converted into point clouds to take advantage of point cloud processing techniques. This conversion is often done using a process called mesh decimation, which reduces the number of triangles in the mesh while preserving its overall shape. Once the mesh has been converted into a point cloud, we can apply any of the subsampling methods we discussed earlier to reduce the size of the point cloud and make it more manageable to work with. This can be particularly useful when working with large or complex meshes, which can be difficult to manipulate in their original form. In conclusion, subsampling is an essential step in managing and processing large-scale point cloud datasets. The different subsampling methods we discussed in this presentation allow us to reduce the complexity of the data while preserving its essential characteristics. By using these methods and taking advantage of the scalar field, we can obtain high-quality subsampled point clouds that are suitable for various applications, such as 3D reconstruction, visualization, and analysis. Thank you for your attention.